Welcome to lesson 1-2, measuring and constructing segments. Actually, we're going to hold off a little bit on the constructing until we have a day just to play with the compasses and rulers. So our primary learning targets for lesson 1.2 is going to be focused around segments, being able to set up and solve problems involving length and midpoint of a segment, and being able to write proofs as a basic with basic geometric figures of segments and midpoints. The ruler postulate from 1-1 says that if you have points, you could align them to numbers on a ruler. That if you have 2 points, you could set a ruler to them and assign numbers. Assign measurable units. Two points using a ruler. So in this case, if I assign A, like here's my point A and my point B, I drew them there intentionally, and I then put my ruler down and said, well, hey, A is at 1 and B is at 3. Then the distance between the two of them would be the absolute value of 3 minus 1, or the absolute value of 1 minus 3. Just take the difference of the two numbers that are assigned and take the absolute value since we're talking about distance. So here we get a distance of 2 and here we get a distance of 2. Those two, A and B, the distance from A to B is 2 units, or actually in this case 2 centimeters if that were actually to scale. All right. So now we talk about distance. So we had talked about the distance between 2 points can be measured, and sometimes it's just by numbers that are assigned. Now there is a specific formula that we can use later when we're looking at points in the coordinate plane, but for right now we're looking between 2 points that can be measured using the above. If we have numbers assigned, we can take the difference of their numbers that are assigned and do the absolute value. Length is the same thing as distance between 2 points. Okay, so the distance of, or length of, AB is 2, and rather than writing it out like that, we can just write AB equals 2. Here's our first example on how to apply this. Example 1, finding the length of a segment. To find the length of segment BC, we have to look at the numbers that are assigned, 1 and 3. I usually do larger minus smaller, but you could do smaller minus larger. Doesn't matter, you're going to do the absolute value because distance is always positive. Oh, that might be a note that I wanted to make here. Distance is always positive. Now there are some cases when we get to pre-calculus where you might have a negative radius and all that means is it's on the other side of a pole, but you'll get there when you get there. For now, for geometry, all distance is positive, even if we're going in a negative direction. So if I'd gone from 3 to 1 or 1 to 3, it wouldn't matter. It's still 2 units apart. The distance between A and C, so -2 minus 3, I'm just going to take those assigned numbers and subtract them. That is -5, and the absolute value of that is 5. So 5 units between points A and C. So AC equals 5, BC equals 2 units. AC equals 5 units. Congruent segments. Congruent means having the same measure. So congruent segments are segments that have the same length or the same distance. Now we mark those with tick marks. So if we had AB and let's see if we can draw this correct. They don't have to be parallel, but let's say that those were the same length. We would use a single tick mark in the center of them to indicate that those are congruent. And then the notation we would use would be, we would say AB is congruent to CD. This little symbol here, the equal sign with a tilde on top, is the symbol for congruence. Is congruent to is what it means. Now, if I had two additional segments, maybe we call them XY and WZ, and they don't have to be parallel, I'm just drawing them that way, and they were also congruent. Well, then I couldn't use one tick mark because that would mean that they're also congruent with this and they're not. So I'd have to use two tick marks, double tick marks, to show that XY is congruent to WZ. Segment XY is congruent to segment WZ is how that is read. And if I had yet a third, then I'd have to use three tick marks if they weren't the same as these, and four tick marks, and so on. So that's congruent segments. Now we're going to look at the segment addition postulate. You have a line segment. We'll call it AC. And B is between, on a segment, and our example is AC, a point, in our case B, is between A and C. And we're going to put a big if in front of this. You'll see why later when we get to proofs. This is going to be a conditional sentence. If these conditions are true, then there's going to be a certain equation that's true. So let's talk about this though. If on a segment AC, a point is between A and C, then these things are true. Now when students draw this, a lot of times they just put B right in the middle. But then they get confused because when we get to midpoint, which means that it actually is in the middle, it cuts it in half, then they're like, well, wait a second, am I drawing this or am I drawing segment addition postulate? So if it doesn't say midpoint, my suggestion is wherever you think the midpoint is, go to the left or the right to draw the point when it says it is between. Do not put it in the middle when the words are between, when it says the point is between. Because otherwise you're going to set up the problem wrong. So what this means is, remember we could assign a distance to this, this, and even this? Well, if I have a defined distance from here to here, and a defined distance from here to here, by the way, this distance being the distance from A to B, maybe it's 2 units. Let's pretend that it's 2 units, even though it's not. Okay, so there's 2 units. And there would be 3, 4, 5. We'll pretend that that's evenly spaced. That would be 6. So if this is 1, and this is 2, and this is 6, the distance between B and C is 1, 2, 3, 4 units. So BC is 4. Then what is the distance from A to C? Well, that's easy, Mr. Ritter. It's 1, 2, 3, 4, 5, 6. Yeah, it is. Or 2 plus 4. We're basically taking this segment's distance and this segment's distance and adding them together to get the whole thing. AB plus BC. So the equation that we would say is that if B is between A and C, so A and C are the endpoints and B is somewhere in between them, not necessarily the middle, then AC, the distance from A to C, equals AB plus BC. This is the segment addition postulate. And a postulate is something that is assumed to be true without proof. We don't have a way to prove it other than using numbers and visual examples. We can't prove that it's always true, but we can't prove it's false either. So it's something that we assume to be true without proof. We'll talk about postulates versus theorems later. So segment addition postulate, if you got a point between two others, then that piece plus that piece adds up to the whole distance. Using the segment addition postulate. G is between F and H. So a lot of times in geometry we have to draw pictures to represent the situation because they didn't give us a picture for this one. between F and H, that means F and H are our endpoints. And we're putting G in between them, so not exactly in the middle, a little off to the side. They tell us that FG is 6, and FH, the whole thing, from F to H, is 11. And we're supposed to find GH, which I'm going to call X. Well, using the segment addition postulate, which I abbreviate seg add post for segment addition postulate, FG plus GH should add up to FH. This piece of the whole segment plus this piece equals the whole thing. Piece plus piece equals the whole thing. So we have 6 plus X equals 11. We can solve. X equals 5. Now some of you just knew the answer in your head anyhow, but we are supposed to start with the segment addition postulate as we set up these statements. So I'm going to do that for letter B, and I'm going to write it as a proof this time, which is kind of like what I did here, except I'm going to have, just like we had with our algebra, statements and reasons. So I'm looking at this, it says O is between. Now they did something bad, they put it right in the middle. That's not good, because then somebody's going to go thinking those are equal. They didn't say it was the midpoint, so I can't say they're equal. O is between N and P. I'm going to change that. I'm putting O right there. I don't like that. All right, so that's a big no. Don't put it in the middle. All right, NO. So the statement I'm going to write is about, hey, why am I going to be able to make an equation? Yeah, there's the whole thing, NP, and here's the pieces. So the equation I'm going to write to start is NO, piece NO, plus piece OP equals the whole thing, NP. How do I know this? What says we're allowed to say that? Well, this is basically right here the segment addition postulate. So that is my reason, segment addition postulate. And if you put seg add post, that's fine, I'll accept that. So that's our first step. Hey, I'm setting up this equation because Euclid's segment addition postulate tells me I can. Now I'm going to plug in the numbers. NO is 17. OP is 3x minus 5. And NP, the whole thing, is 5x plus 2. So here's my statement number 2. How did I do that? I plugged it in. There's a math word for plugging in. It's called substitution. Now I'm just going to solve. So first I'm going to combine like terms to get my next equation. So that leaves me with 3x plus 22, plus 12 equals 5x plus 2. So my this step to go from here to here, I combined like terms. Your book calls it simplify. I prefer for you to write what you actually did. Did you distribute? Write distribute. Did you combine like terms? Write CLT. Now I'm going to subtract 3x from both sides. You're welcome to show the work in between, but it doesn't get its own numbering. The numbering is the new equation. So this would be 12 equals 2x plus 2. And that is going to be, since I subtracted it, is the subtraction property of equality, POE. We can abbreviate, but we still say it as it is. And I'm going to bring it down here a little bit because I need more space. So number 5, I'm going to subtract 2. I get 10 equals 2x. Again, I used the subtraction property of equality. Remember to say property of equality. You don't say that you live in Commerce, Me. You say Commerce, Michigan, even though it's abbreviated MI, capital M, capital I. Line 6, we divide by 2, so we get 5 equals x. And that would be division property of equality. And that almost completes our proof. Technically, we should have one more line flipping this, saying x equals 5, symmetric property of equality, but I'll be okay with this as long as you get the answer for x. And actually, we need more, so there actually is one more step, because we're supposed to find NP. Well, NP is 5x plus 2. But we know what NP is. or what x is, it's 5. So that's 25 plus 2, which is 27. And so we would write this as substitution again because we're plugging it in. So I know that's long and complicated, but we're going to practice this every once in a while with some problems here and there. So when we get to the geometric proofs that are tougher, we're used to the steps. So all we started with was, what equation can I write using the segments, NY, segment addition postulate, plug in the expressions, that substitution, go through the solving process using all the things we used with our algebra proofs, and plug it back in for whatever they ask for. Be very careful on a BA or a quiz to make sure that when you think you have the answer, I can't tell you the number of times people have told me x equals 5 is their final answer. That's not what they asked for. They asked for NP. So we have to take that and plug it back in to give our answer. Let's take a look at letter C as a proof. And let me draw my picture over here. We have O is between Y and U. And I'm going to put O off to the left just a little bit. They tell me that OY is 3x and that OU is 5x minus 4 and that the whole darn thing is 12x minus 20. Take a second to see if you can write this or at least set up the initial step. Welcome back. Hopefully, if you did this correctly, you did the following. You started by having statements and reasons, and for time's sake, I'm just going to put S and R, and you can put that. We have YO plus OU equals YU. And how can we write that? By the segment addition postulate. That's our first equation, so it's numbered with a 1. Now I'm going to plug in those expressions. So for YO, I have 3x. For OU, I have 5x minus 4. And for YU, I have 12x minus 20. The reason for that particular line is plugging stuff in, so you guessed it, substitution. Now I'm just going to go through the solving process. So combining like terms, I have 8x minus 4 on my left-hand side and 12x minus 20. Because I combined like terms, I put CLT. If I distributed, I would have write distribute. Now I'm going to get my variable to one side by subtracting 8x from both sides. That leaves me with negative 4 equals 4x minus 20. I got that by using the subtraction. It is one that we have to write out, unfortunately, so we don't confuse it with substitution. Property of equality. Next, I'm going to add 20 to both sides. This is going to give me 16 equals 4x. So for my fifth line, that's my equation. To get from line 4 to line 5, I added 20, so I used the addition property of equality. And lastly, I'm going, well, not lastly, but in the solving process, lastly, I'm going to divide by 4, giving me 4 equals x. And we divided, so we used the division property of equality. Now I'm going to go back, now that I have my answer, and see what they wanted us to find. They wanted us to find YU. So my final line is YU equals, and I'm going to plug this in, YU's expression is 12x minus 20, and x is 4. So 48 minus 20 is 28. There's my answer to the question they were asking. Written as a proof, the last justification would be substitution. Please go on to the next video for examples 3 and 4.